Welcome back to Q Point. An understanding of high pass and low pass RC circuit is necessary for further discussion of analog circuits. So we study the RC circuits first and then proceed to analog circuits part. In this current lecture, we study the step response of high pass RC circuit. Before entering into the topic, I wish to make some acknowledgements. The following free softwares are used in preparing this lecture. The slides are prepared on LaTeX Beamer. Screen recording is performed on Simple Screen Recorder, an open source application. Video editing is done on Shortcut Video Editor. Simulations are performed on the Qucs-spice. The OS used is Debian 12 Bookworm. I express my deep gratitude to the creators and maintainers of the above softwares. Let us now look at the RC circuit, which is known as the high-pass RC circuit. We know the capacitive reactance is low at high frequencies. So, in such a circuit, if the input contains many frequency components, the high frequency components will pass through the capacitance with low attenuation compared to the low frequency components. That is the reason why this is called a high pass circuit. High frequency components are passed easily through the capacitor compared to low frequency components. Another name for the circuit is a high pass filter. At extremely high frequencies, the capacitor acts almost as a short circuit and the input is almost fully passed to the output. At zero frequency, that is at DC, the capacitor has infinite reactance and behaves as an open circuit. We say that the capacitor blocks DC. Now assume that the input voltage Vi is a step input. For analysis of the circuit with step input, we define a unit step function as ut equal to 1 for t greater than or equal to 0 and equal to 0 for t less than 0. The function is plotted here. You can see that the value of the function is 0 for t less than 0 and 1 for t greater than 0. This function mathematically replaces a switch activated at t equal to 0. Suppose we want to apply a voltage, say 5 volt at t equal to 0 to a circuit. We represent this in the circuit diagram as a 5 volt source in series with a switch which is closed at t equal to 0. But if you specify that the input is 5 ut, you can remove the switch because 5 ut is applying a 5 volt for t greater than 0 and is equal to 0 for t less than 0 because of the property of the unit step function. The time immediately before t equal to 0, that is this time, immediately before t equal to 0 is usually designated as t equal to 0 minus, and the time immediately after t equal to 0 is designated as t equal to 0 plus. So at t equal to 0 minus, this function has a value of 0, and at t equal to 0 plus, this function has a value of 1, or if you apply 5 ut at t equal to 0 plus, the voltage is 5 volt. Let the input to our circuit is VUT. V voltage is applied at t equal to 0. Assume that the capacitor is initially uncharged. The current in the circuit is I. So by the application of the voltage, a varying current will circulate around the circuit. We will find an expression for I. What is the nature of I? At t equal to 0 plus, that means after the application of the voltage V, we can apply KVL around the loop, which will give the voltage across the capacitor plus the voltage across the resistance must be equal to the input voltage V. Voltage across the capacitor is 1 by C integral 0 to t I dt. Voltage across the resistance is R into I. So we can write 1 by c integral 0 to t I dt dash plus Ri equal to V. Here t dash is a dummy variable used for not to confuse with the upper limit of the integral. You can use any variable here because the value of a definite integral does not depend on the variable of integration. So we have, say at t equal to 0, we are applying the switch, applying the voltage, and our aim is to find the expression for the current for any value of time. So from 0 to t, 1 by c integral I dt is the voltage across the capacitance. A note here. Here in our problem, it was assumed that the capacitor is initially uncharged. If the capacitance is initially charged, then the limit of integration, lower limit of this integration will be minus infinity, not 0. That means the voltage across the capacitor can now be expressed as 1 by c integral minus infinity to t I dt, which is equal to 1 by c integral minus infinity to 0 I dt plus 1 by c integral 0 to t I dt. This value 1 by c integral minus infinity to 0 I dt will be a constant value, and that value is the initial voltage across the capacitor. Now coming back to our current situation, we have an integral equation here. We can convert this into a differential equation by differentiating throughout with respect to t, resulting in r di by dt plus 1 by ci equal to 0. You can rearrange this equation into this form: di by I equal to minus dt by rc. We say that this equation is in the variables separable form. The variables I is kept on one side and t on the other side. Now integrating both sides. The left hand side is di by I. 1 by I di will give, after integration, natural logarithm of I equal to minus t by rc plus k, where k is a constant of integration. So the solution to our circuit is complete only if we know the value of k. In order to obtain the value of k, we apply the initial conditions. There are certain initial conditions in capacitive and inductive circuits. So to apply initial conditions, we have to know an important property of the capacitor. The voltage across a capacitor cannot change instantaneously if the current is finite. So if a sudden voltage is applied at one plate of the capacitor, at the other plate of the capacitor exactly the same volt will appear, so that there is no potential difference across the capacitance instantaneously. Or speaking in simple language, the capacitor is transparent to very high frequency signals. So if you suddenly apply a voltage at one plate of the capacitor, the other plate of the capacitor also is available with the same voltage. That means there is no voltage change across the capacitance for suddenly varying signals. Or speaking in other words, the capacitor will take some time to make the potential difference across it change. It cannot change instantaneously. Now in the current situation, we have a t equal to 0 minus, our input voltage was 0 because it was step voltage. At t equal to 0 minus, it was 0. And at t equal to 0 plus, we suddenly impress a voltage of V at the left lead of the capacitance, or the left plate of the capacitance. Now by the property of the capacitance, which states that the voltage across the capacitor cannot instantaneously change, this same voltage V should appear on the right plate of the capacitance, so that there is no voltage drop across the capacitance for this change. That means the applied voltage V is now fully dropping across a resistance R, which drives a current I0 equal to V by R. We call the current I0. because it's current at t equal to 0. So we say that initially, immediately after applying this voltage, the current in the circuit is V by R. Now as time goes on, the capacitor will charge and the current in the circuit will change. Our aim is to find an expression for the current. Now coming back to our equation, log I is equal to minus T by RC plus K. In this equation, we apply the initial condition. Put T equal to 0. Putting T equal to 0, this term will become 0 and I will become I0. So putting T equal to 0, we have log I0 equal to 0 plus K, or we get K equal to log I0. So we obtain the value of the arbitrary constant, the constant of integration, which is equal to log I0. Substitute in this equation, we get log I is equal to minus T by RC plus log I0. What remains is only algebraic manipulation, bringing I0 to the left hand side. Log I minus log I0 is equal to minus T by RC, and log A minus log B is log A by B. So by that principle, we have log I by I0 equal to minus T by RC. Now take anti-logarithms on both sides, which will give I by I0 equal to e raised to minus T by RC, or I equals I0 e raised to minus T by RC. And we know I0 is equal to V by R, that is the current at T equal to 0 plus in the circuit. So we have I equal to V by R e raised to minus T by RC. See, if you look at the equation, if you put T equal to 0 in this equation, the current is V by R, as what we have mentioned earlier. So at T equal to 0, this current is V by R. And as time goes on, the current exponentially decreases. You can see the e raised to minus T by RC, the current is exponentially decreasing. So as time increases, the current decreases. What happens is, as time increases, the capacitor voltage increases. This capacitor voltage actually opposes this voltage so that the current in the circuit decreases. So as time goes on, the current in the circuit decreases. That is our observation. So we will plot this expression, the current versus time graph. Plotting that, we get a shape of the graph like this, an exponentially decaying function. Now what is the rate at which the current is falling or current is decreasing is decided by the product R into C. The product R into C has dimensions of time, and we call this as R into C, designated as tau. Try to verify the result. Try to verify that RC has dimensions of t. So if the time constant is high, that implies that more time will be taken by the current to reduce. So time constant gives an idea about the speed with which the capacitor charges. If time constant is high, capacitor is charging slowly. So we can formally define time constant as, say, assume that the capacitor were charging linearly. So assume that the capacitor charges at the same rate at t equal to 0. So if you plot a tangent at t equal to 0 to this, the tangent will meet on the time axis at tau, at time constant. So if the current were decaying initially linearly at the initial rate, it would become 0 in one time constant. That may be used as a definition for time constant. Other definitions are possible. Now, since the current decays exponentially, it will become 0 only at t equal to infinity. For any finite value of time, the current will not be equal to 0. See, we will calculate the time at different values of time constants for at t equal to RC. That is, after one time constant, I is equal to e raised to minus 1 V by R equal to 0.368 V by R. That means at one time constant, the current in the resistance or the output current will drop to 36.8% of its initial value. So that also may be used as a definition for the time constant. Time constant may be defined as the time taken by the current to drop to 36.8% of its initial value. That is another definition possible. So at the one time constant, the current becomes 36.8% of the initial value. So you can see the current is decreasing continuously up to t equal to infinity. So it seems that the circuit never reaches steady state. But at t equal to 5 RC, if you calculate the current, this is equal to 0.006738 V by R. It is only 0.67% of the initial value, a current which is almost negligible. So even if the current becomes zero only at t equal to infinity, we say that the current is zero practically at t equal to 5 RC or for times greater than 5 time constants. So for time greater than 5 time constants, we say that the current is equal to 0 and we say that the circuit has entered steady state. Before steady state is reached and after the application of the input, we say that the circuit is in the transient state. So immediately after the application of a signal, the circuit will take some time to reach to the steady state. This time is decided by the product RC. That is the significance of the time constant. If you have less value of RC, the circuit will reach steady state fast. And if you have high value of time constant, the circuit will slowly reach the steady state. It will take more time to reach the steady state. Now we will find the voltage across the resistance and so voltage across the capacitance. The voltage across the resistance is the current flowing through the resistance multiplied by the resistance value. Current flowing through the resistance is V by R e raised to minus t by RC, which is multiplied by R. So we will get VO equal to V e raised to minus t by RC. You can see that this also has the same form as the current, an exponentially decaying function with initial value as V. V is the applied voltage. So at the instant of applying the voltage, the full voltage is now dropping across the resistance R. So if you plot the output voltage versus time, you will get the same or a similar graph for the plot of current. Now we will find the voltage across the capacitor. The voltage across the capacitor is 1 by C integral I dt. That is our expression. So 1 by C into V by R integral 0 to t e raised to minus t dash by RC dt dash. Here also we use the dummy variable so that this t dash and t are not being confused. So integrating, what we get is V by RC into e raised to minus t dash by RC between 0 and t into minus RC. So simplifying, you will get this as Vc equal to 1 V into 1 minus e raised to minus t by RC. So this is different. This expression is different. For the load voltage or the output voltage, it was an exponentially decaying function V e raised to minus t by RC. In this case, it is V into 1 minus e raised to minus t by RC. So 1 minus this exponentially decaying function is an exponentially rising function. Let us plot all the waveforms. Plot the output voltage and voltage across the capacitor along with the input. This will be the plot. So this is the voltage across the capacitor. it is exponentially rising and finally reaching the value of V. See, it will reach the value of V only after infinite time, but practically we can say that after 5 time constants, its value is equal to V. At the same time, the current through the circuit is 0. So what actually happens? In this circuit, the capacitor charges. There is a current flowing through the capacitor, and when the current is flowing through the capacitor charges and the voltage across the capacitor rises. When the voltage across the capacitor rises, the current in the circuit reduces. So as the voltage across the capacitor increases, the current through the resistor, that is the output, decreases. And finally, the current through the resistance and hence the voltage across the resistance becomes 0 after 5 time constants. That means no DC current is entering to this. At this situation, we say that the capacitor blocks DC. So in the transient time, the capacitor allows some current, and in the steady state, after steady state has reached, the capacitor blocks DC. So you can see the capacitor charges exponentially towards V with a time constant R into C. The speed with which capacitor charges is decided by the time constant RC. The lower the time constant, the faster the capacitor charges. Now, I am giving a table here. We will calculate the value of Vc as a fraction of V and Vo as a fraction of V for different time constants. For one time constant, the capacitor voltage reaches 63.2% of its final value. This is the final value V. So that also may be regarded as a definition for time constant. Time constant may be defined as a time taken by the capacitor voltage to reach 63.2% of its final value. At that time, you can see the output voltage is only 0.368 or 36.8. It reduces. And after 5 time constants, you can note that the capacitor voltage is 99.3% of the final value. And the load voltage, the output voltage is only 7% of its initial value. So the output voltage is almost 0 and the capacitor voltage is almost equal to the input voltage. That is a conclusion. So after 5 time constant, capacitor voltage reaches 99.3 of the input. Okay. So after getting fully charged, no further DC current is allowed, and we say that the capacitor blocks DC. Let us simulate our circuit. I am using the Qucs-spice for simulation. This is an open source simulator available. And this is the board where you are wiring the components, wiring the circuit diagram and performing the simulation operation. Our circuit contains one resistor and one capacitor. So we require two passive components. So go to the components menu at the left side of the screen. Then select resistor. By simply clicking on resistor and moving the mouse, the resistor follows on your mouse tip. To place the resistance on the board, click it anywhere on the board. Now it is placed there. And after this, if you are moving the mouse, you can see that the resistor again follows. Another copy of resistance follows. So you can place any number of resistance here. Presently, we require only one resistor. So to terminate this operation, press the escape button. Then place a capacitor. Press escape. Now for our circuit, we require our resistor to be rotated. So click on the resistor. Resistor is selected. Either you press Ctrl R or right click on this, rotate. You can drag the component and place it anywhere on the board. Now what remains is a source, a voltage source. So go to sources menu, take a voltage pulse. This is actually a pulse. We are converting this into a step voltage. So that is again placed. Now we require ground. Ground is available on the top ribbon, or ground is available from the insert menu. Insert ground, or by pressing Ctrl G, ground is available. Click on that. Ground is placed. Now we have to wire the circuit diagram. So this is a wire. It is on the top ribbon, or again it is possible to go to insert, wire, or press Ctrl E. So by selecting the wire, you can see that your mouse tip now changes into a cross wire. Click on the point where you want to fix the wire. Click and click here. Now the wiring is complete. Press escape. Now what we require is we want to edit the values, and before that we will save the circuit. Click on save. Click on any convenient place and give any name. I give the RC circuit 1, RCC1 as the name. Save. Now you have to edit the component values. There are two methods by which you can edit the component values. One way is to click on the component, select on it. So the component is selected. Right click, go to edit properties, and a number of properties are given here. See TC1, TC2, these are all temperature coefficient values. We are not interested in that. We will change this resistance to say 1 kilo ohm. Simply write 1K and apply. Okay. Another way of editing the component values is simply click on the value of the component. Let this be 1 microfarad. Type 1U and press enter. This point is important. Unless you press enter, that value will not be modified. So type the new value here and press enter. Now we will edit the source, the pulse source. Actually it is a pulse. A pulse remains low for some time, then it goes high, then it again returns to the low value, and so on. We require a step function which has a low value, and at t equal to 0 it goes high and it stays high forever. That such a signal is required. So we will use a strategy that the on time of the pulse, the duration for which the pulse value remains high, is made much higher than 5 times the time constant. We know after 5 time constants circuit becomes stable. So after that there is no point in keeping the signal infinitely long duration. It should stay high at least for 5 time constants. So we will make it, say our time constant in the circuit is 1 millisecond. We will make it high for 10 millisecond. Then that is equivalent to a step function or step voltage. See, these are the properties of the voltage sources. The pulse source given. U1 is the low value. T is equal to 0 is by default. So we are not changing it. U2 is the value at which the signal is high. So let it be 5 volt. T1 is the duration for the low value. So we are not changing it. Default value is 0. That means at t equal to 0 the signal goes high. And this value we will edit. Assume that T2 is the duration for which the signal remains high. Assume it to be 10 milliseconds. So that this time is higher than 5 time constants in the circuit. That is the strategy that we are using. So 5 milliseconds is our time constant. We are making this 10 milliseconds. So this is as good as a step voltage. Click apply, click OK. So all the settings are over. What remains is to simulate. So what we have done is we have placed the components, wired the components, saved our circuit and edited the values. Now we will simulate. For that, you go to the simulations menu, simulations. Click on that. Then the possible simulations are displayed on the left side. Click on transient simulation. It follows on your mouse tip. Place it on the circuit diagram anywhere on the board. This step is very important. Unless you are placing this panel on the board, simulation is not possible. So you have to pick it from the menu and place it on the board. Then only simulation is possible. Now we want to edit. Select this, right click, edit properties. Start value is 0. Stop value is, let it be 8 milliseconds. It should be at least 5 milliseconds for 5 time constants. We are making time a bit more higher. Step is, let it be 10 microseconds. So that sufficiently closer values are obtained to plot the graph. Apply. So you can see by selecting 10 microseconds, you will get 801 points, number of points to plot the graph. Okay. Now, our settings are over. We have, our circuit has a 1 millisecond time constant. We set the pulse to remain 10 millisecond, which is much higher than 5 times the time constant. The circuit is in a stable state or the steady state. And we are running the simulation for 8 milliseconds, again greater than 5 milliseconds, 5 times the time constant. Now go to simulation, click on simulate or press F2. The circuit will be simulated. Now the simulation is over. Now what we require is, we want to observe some values. So we haven't specified which values that we want to observe. So we will add some labels to this circuit. This is the name label, wire label. Click on it, place it here. Let us give the name VO. This is our input voltage. Give the name VI. Okay. This step you should have done this step earlier before simulating. So once again simulate, press F2. Now we want to observe the waveforms. The waveform is observed on Cartesian plane. Along the horizontal axis you are plotting time. Along the vertical axis you are plotting either voltage or current. So you take a Cartesian graph from here, place it on the screen. Now the display window is appearing. We want to observe VI and VO. So double click on VI. Single click is not enough. Double click on that so that value will be displayed here. We will change the thickness to 3. Then we require VOT also. Double click on that. Apply. OK. Press escape. So this is the graph that you are going to observe. We will expand this time scale. So you can see that this is the voltage. This is the voltage, the output voltage, and the blue is the input voltage. So remember our time constant is 1 millisecond. So after 5 milliseconds, the circuit is in the steady state. The current is almost zero at 0.005 seconds, that is 5 milliseconds. Thereafterward, the current approaches zero and it is almost zero. You cannot separate it from zero. It's very close to zero after 5 time constants. So this is the output voltage. Now, suppose you want to measure the input voltage. Again, the input voltage is here, the output voltage is here. Suppose you want to measure the voltage across the capacitor. For that, you have to use a voltage probe. Connect a voltage probe here. So go to the probes menu, probes, select a voltage probe, place it on the board, press escape and then wire the probe. Press escape. Again, run simulation, press F2. Now you can add that on this same window or you can take another window. Say for example, if I am taking another window, place it here. This is probe 1. Double click on this. Apply. Okay. Press escape. So along with this, let us plot the input also, or let us add the same plot on this. So that we can compare the results. So all the plots are added here. We will delete this. So this is the voltage across the capacitor and this is the output voltage. You can see the capacitor charges exponentially and reaches the final value, that is 5 volt here, after 5 milliseconds. See, after 5 milliseconds is 5 time constant. You can see the voltage, the capacitor voltage reaches 5 volt and at the same time the output voltage decreases to 0. Because circuit obeys Kirchhoff's voltage law, voltage across the capacitor plus the voltage across the resistance must be equal to 5. So if the voltage across the capacitor increases, the output voltage reduces. That is what the observation that we see here. Now assume that we are changing our resistance from say 1K to 500 ohms. Again run simulation. You can see that the capacitor charges now fast. Now the time constant is small. So at a lower value of time, the circuit reaches steady state. So if the time constant is less, the capacitor charges faster. Now, if you want to measure the current through the load resistance, the output current, you have to add a current probe here. So let us place another probe. Go to probes, select a current probe and place it here. Click and press escape. Now current probe is placed, that is probe 2. Run simulation, press F2. Now we will add another window, another Cartesian plane. Now we are plotting the current. You can see the current reaches 0 after 5 time constants. At t equal to 0, the current is almost 0.01 amperes. So what will be the current? 5 volt by 500. So it is 1 by 100.01. That is what you are seeing here. And the current exponentially decays to 0 and after 5 time constants the current is almost 0. So these are the observations. These are the theory that we have studied, and we observe these parameters. You can see capacitor charges exponentially, and when the capacitor voltage rises, the output voltage falls. Because the circuit always obeys Kirchhoff's voltage law, the voltage across the capacitor plus the voltage across the resistance must be equal to 5 volt at any instant of time. At any instant of time, if you find Vc plus Vo must be equal to 5 volt. And as the output voltage drops to 0, the output current also is dropping to 0. So that's all about the simulation. So this is the conclusion. The key takeaways from this lecture. 1. A high pass circuit passes high frequency signals with less attenuation than low frequency signals. A voltage across a capacitor cannot change instantaneously. You can prove it mathematically. The product RC is known as the time constant of the circuit and is measured in seconds. The capacitor charges exponentially with time constant RC. We have seen this. If RC is large, capacitor slowly charges. If RC is less, capacitor charges fast. The time constant is the time taken by the capacitor voltage to reach 63.2% of its final value. So here one point you have to note is time constant is not the time taken for the capacitor to get fully charged. It is not time constant. Time constant, in one time constant, the capacitor voltage will reach only 63.2% of its final value. For the capacitor to get fully charged, it requires 5 time constants. So don't think that time constant is the time required for the capacitor to get fully charged. It is not so. Time constant gives an idea of the speed with which the circuit reaches steady state. The circuit is assumed to be in steady state after a time equal to 5 RC, or after 5 time constants, the circuit is assumed to be in steady state practically. And the capacitor blocks DC from reaching the output. Thus, even if the input signal contains a DC value, the output has only the AC components in the steady state. All the DC components from the signal will be removed by the capacitor. So in that sense, this capacitor is called a blocking capacitor. So it is blocking DC. You can see the blocking application of capacitors in amplifiers. Similarly, this is used for coupling one stage of amplifier to the other. We care for capacitively coupling. Again, we are using the same property. The DC is blocked. So that is enough for the day. We will find the references. There are 4 references given. Thank you. We will meet with the pulse response of high pass RC circuits in the next lecture.